This lecture will be an introduction to aromatic compounds, including their structures, how we name them, and a few of the chemical reactions that they can undergo. When you think of the word aromatic, right away you probably think about something that has an aroma or a smell. And in fact, this is originally where chemists did get the name for aromatic molecules. Scientists noticed that certain organic compounds tended to have very distinct aromas. In the modern age, however, our definition of what an aromatic compound is has gotten far more technical. And in fact, it's so technical at this point that it goes beyond any of the topics that we'll cover in this class. It's still possible to understand aromatics in general, however, by thinking about them as molecules that are based on a simpler structure called benzene. So many scientists consider aromatic molecules to be benzene and benzene-related compounds. Benzene itself actually has a relatively simple yet interesting structure. Here's one way we can draw the structure of benzene on paper. Right away you notice it is a cyclic carbon compound. It contains 6 carbons and it would appear to contain 3 double bonds. We also know that because it's a line structure, there's 1 hydrogen on each of those carbons. So its chemical formula would be C6H6. Notice that I drew these 3 double bonds in alternating positions. You could just as easily have moved them all by 1 position and gotten the molecule on the right. Technically, these are equivalent molecules. Now here's what's interesting about benzene. As scientists started to explore the properties of benzene, they noticed something interesting. Even though benzene appears to have 3 double bonds, it doesn't react at all like other alkenes. It's almost like something must have been wrong about their understanding of the structure. And in fact, as our science advanced and we were able to actually measure the length of the bonds in benzene, we noticed that the bonds didn't seem to correspond to single and double bonds. We expect that carbon-carbon single bonds are longer than carbon-carbon double bonds. And yet when we look at benzene, it's a completely symmetric molecule. All of the bonds are identical in length. The length of the bonds actually corresponds to basically a 1.5 bond, something between a single and a double bond. Scientists now understand that the reason for these observations is that the way benzene exists in nature is a little bit of a hybrid between these 2 drawings we have in front of us. These are what we call resonance structures. They're basically ways that we attempt to draw a molecule, even though we know that in reality, the molecule is actually an average of the forms we can draw on paper. So in reality, we don't have alternating single and double bonds. We have an average size bond all the way around that's roughly equivalent to a 1.5 bond. You can still draw benzene by drawing alternating double bonds, but some people like to use a little bit of shorthand. The shorthand is to draw the 6-membered carbon ring and then draw a circle inside it. The circle is used to indicate that we're dealing with a benzene molecule. Benzene is interesting for a number of reasons. As we'll see in a couple minutes, as an aromatic, it's the basis for many, many molecules around us. What's also interesting is that they don't act like alkenes. They basically have their own chemistry. Now that 6-membered carbon ring is one of the most stable structures that we have when it comes to cyclic ring structures. And in fact, we see this 6-sided ring, called a hexagon, in many places other than just chemistry. For one, bees make their honeycombs out of hexagons. So as a chemist, when I look at a honeybee's honeycomb, I see benzene rings. In fact, carbon isn't the only place that we see these hexagon shapes. Water molecules, even though they're far more simple than a 6-membered ring, form 6-membered rings when they start to freeze. This is why ice has a hexagonal shape when we view it at the molecular level. The consequence of this is that things like snowflakes and ice crystals tend to have 6-sided rings when we look at them under an electron microscope, as I'm showing you here. Finally, one more interesting place where we run into these six-sided rings is in certain types of architecture. Hexagon-shaped rings can be used if you want to create a wall that's porous, or if you want to create a window that doesn't actually have glass, or that has better ventilation. This is actually part of a window of one of the most famous buildings in the world. Do you recognize it? What about now? If I pull out a little bit further, does it start to seem familiar? I'll give you a hint. It's somewhere warm enough that you wouldn't need glass windows to keep the cold out. Get it yet? Okay, well now you should know that this is the Taj Mahal in Agra, India, one of the most famous buildings in the world, and all of its windows are actually made up of repeating hexagon patterns. So of course, when I was lucky enough to be at the Taj Mahal, all I could think is, woo, benzene rings! More proof that chemistry is absolutely everywhere around us. So the 6-carbon structure of a benzene ring is something we see in a lot of places. And in all seriousness, it's not just a lot of places around us, it's also in a lot of different molecules. We said that aromatic molecules are based on the benzene ring. Well, there's many variations. If you add one extra ring and place it directly next to the benzene ring, you get a molecule that's called naphthalene. Naphthalene can be used as a fuel, like most hydrocarbons, but you might be most familiar with it because it's used in mothballs. This structure, which contains a benzene ring with some other functional groups attached, is acetyl salicylic acid, better known as aspirin. It's an aromatic compound, and you can recognize that because it does have a benzene ring in it. Here's another compound that actually has 2 benzene rings. As we'll see in a minute, when you attach that OH group to a benzene ring, you have what's called a phenol. And this particular molecule is bisphenol A, better known by most people as BPA. It's the additive in some plastics that many people are trying to phase out. Here's a molecule we saw before, testosterone. Notice now that testosterone, like all steroids, has 3 benzene rings. We can't see all the double bonds that we're used to seeing in benzene, but again, that's partly because there's a more technical explanation of what actually makes things aromatic. Let's look at just 2 more compounds, which are very similar to each other. Both of these compounds would be considered aromatic molecules, and you can see a little bit of the backbone of a benzene ring in both of them. What's the difference between these 2 molecules? Well, you might have noticed the molecule on the left has a methyl group attached to the nitrogen, where the molecule on the right only has a hydrogen attached to that nitrogen. These 2 molecules are caffeine and theobromine. Of course, you already know caffeine as being a central nervous system stimulant. It's the compound that's present in coffee, tea, chocolate, and many other compounds that makes you feel alert. Interestingly, the compound on the right is theobromine. Theobromine is a cardiac stimulant, and it's what's found in chocolate that makes your heart race. In reality, there's probably not enough of it to do that, but I will tell you it's also the compound in chocolate that makes it dangerous to dogs. We'll talk more about both of these compounds later on. So let's talk about how to name these aromatics. Obviously, if you're looking at a benzene molecule, its name is simply benzene. But benzene itself can also have many substituents. The most common aromatics have very common names, and in fact the more complex a molecule is, the more likely it is we just refer to it by a common name. I want to show you some of the most common aromatics and their names, and before I do that, let me assure you you're not memorizing all of these today, or tomorrow for that matter. Here's some of the most common simple molecules that are based on the benzene ring. The only 2 I want you to memorize right now are the first 2, toluene and xylene. Toluene is simply a benzene ring with 1 methyl group attached to it. Xylene is a benzene ring with 2 methyl groups attached. And because we haven't talked about any of the other functional groups other than alkanes, alkenes, alkynes, and aromatics, you don't need to learn the rest of this chart quite yet. But just as a preview, and because you might recognize some of these terms, we'll see later on when we study the alcohol functional group that phenol, PHENOL, is simply a benzene ring with an OH group attached. OH is the alcohol functional group. When we study the amine functional group, we'll learn that aniline, or aniline, is a benzene ring with a nitrogen and 2 hydrogens, which is usually the backbone of the amine group. We'll also see benzaldehyde, benzene with the aldehyde functional group attached, and benzoic acid, benzene with the carboxylic acid functional group attached. Again, for now, just learn the first 2, although if you want to get a head start, we will learn all 6 of these molecules during the rest of the quarter. So with simple molecules, you might have benzene, you might have a simple molecule with a common name like toluene or xylene, but you can also just name benzene aromatics based on whatever their substituents are. If you have one substituent, you might know a common name, or if not, you just use a branch name, the same way we would for any of the other IUPAC names we've learned this quarter. For instance, try this one. Well, we saw on the previous page that one way you can name this molecule is by calling it toluene. That's the common name, and it is accepted by IUPAC, meaning you can use it in any circumstances you want. If you didn't know that, however, it would also be okay to recognize that this benzene has a methyl group attached to it. So as a result, we can name it the same way we've named most branched compounds. We'd call this methyl benzene, a methyl group attached to the benzene ring. Here's another example. Try this one. To name this molecule, you have to identify the substituent. The substituent in this case, or the branch, has 3 carbons, and it's connected to the carbon that's in the middle. So while we know 3 carbons on a branch gives us the prop prefix, we know that because it's connected in the middle, this is the isopropyl branch. So we would call this molecule isopropyl benzene. Things get a little more complicated when we have 2 substituents. Of course, we'll still need to name each substituent based on whether it's a methyl, an ethyl, or other type of branch. But what we have to do now is designate the relative positions of these branches to each other. And we use a shorthand way of doing that with aromatics that doesn't involve numbering, although you will see numbering on more complex examples. But for just 2 substituents on benzene, what you'll see most often is the use of the following terms. If you have a benzene molecule that has 2 branches right next to each other on the molecule, we say that because those branches are next to each other, they're in the ortho position. So when you name the molecule, instead of putting a 1, 2, or any other number in front to designate the position, we would put the word ortho, or the abbreviation O. I'll show you an example in a minute. If we step those branches 1 more carbon apart, so essentially there's 1 carbon in between them, now we're in the meta position. And you can write the word meta as a prefix, or you can write an M. Finally, if your branches are on opposite sides of the benzene molecule, we say that they're in the para position. And again, you can write the prefix para, or you can use the abbreviation P. Let's see these ortho, meta, and para designations in use. Here's an example of a di-substituted benzene ring. It has 2 substituents. I counted that there's 4 different ways to correctly name this molecule. Why don't you go ahead and name it one way, whatever way you're most comfortable with. Okay, in this molecule I have 2 branches. One is the ethyl branch and the other is the methyl branch. I'm going to start with the longest possible name I could come up with and work my way to the shorter and maybe more clever names that you could also use. All of these names would be completely acceptable by IUPAC standards. The simplest way to name this molecule is probably to just look at what your branches are, put them in alphabetical order, then add the appropriate prefix and the ending benzene. In this case, I have an ethyl branch and a methyl branch. But what position are they in relation to each other? They're on exactly opposite sides of the benzene ring, so I say they're in the para position. So one way I could name this molecule is by calling it para ethyl methyl benzene. We offset the para from the name using a dash. Likewise, we could simplify a little bit by writing the letter P instead of the entire word para. That's just as acceptable. So then my name would be P-ethylmethylbenzene. Now there's two other ways you could name this using a shortcut. And the shortcut is to fall back on the common names we talked about a few minutes ago. We saw toluene and xylene. Toluene is the benzene ring that has one methyl group. This is essentially a toluene that also has an ethyl substituent. Therefore, I could name this molecule as para-ethyltoluene because the toluene name includes methylbenzene. Likewise, I could also just call it p-ethyltoluene. So depending on the way you think, either the very first option on here or the very last option on here might be your favorite. The very first one is the simplest because it doesn't require any memorization, any tricks, or any shortcuts, but it does give you the longest name. Honestly, the one that most chemists would use is the one on the bottom, p-ethyltoluene, although if you read it out loud, you'd say para-ethyltoluene. Make sure you try these so you get the hang of it. We won't do anything that's more complex than a di-substituted benzene. There are tri-substituted benzenes out there as well as more complex molecules. And in those cases, most scientists fall back on using a number system, 1, 2, 3, and so on, but we won't do anything that complex in this class. Let's finish up by talking about 3 chemical reactions that aromatic molecules are capable of doing. In fact, because this can be a pretty complex subject, we're only going to talk about benzene itself. So these are really reactions that benzene does, and I won't give them to you with any molecule other than benzene to start because you'd have to know a lot more about organic chemistry to be sure you are writing the correct answer. The first aromatic reaction, or benzene reaction, that we're going to talk about is one that we covered for alkenes as well. It's halogenation. We saw that you can do an alkene reaction with halogenation that adds Cl2 or Br2 to a molecule. The situation is a little bit different when you deal with benzene, however, because we're going to need to use a catalyst. In the case of benzene, you can react it with any halogen, and I'm using X to represent a halogen, as long as you also use the iron catalyst that's related to that halogen. Again, the most common ones that we see are chlorine and bromine. So you can do this reaction either with Cl2 as a reactant and FeCl3 as your catalyst, or you could do it with Br2 as your reactant and FeBr as your catalyst. The product of this reaction is that you add just one of the halogen atoms to your benzene. So in the case of chlorine, you would add just one chlorine atom. In the case of bromine, you would add just one bromine. It's a relatively simple reaction, but it's actually used in a lot of different settings. And one reason is once you attach a halogen to a benzene ring, there's a lot of other reactions you can do from that point. There's also a lot of end products that involve halogenating a benzene ring. This molecule is what you may know as Wellbutrin or Zypan. It's a common antidepressant and it's also used as a smoking cessation agent. Notice that it has a benzene ring because it's an aromatic compound and there's a chlorine attached to the benzene. That means a scientist would have to halogenate the benzene to make this structure. Other important medical compounds like vancomycin, the famous antibiotic, also involve chlorine on benzene rings. But the difference is that vancomycin is a much more complex molecule. Still, as you look at it, you can notice several benzene rings, including 2 of them that have the chlorine atom attached. So halogenation is an important chemical reaction in many industries, especially in pharmaceuticals. Another reaction that a benzene molecule can undergo is what's called nitration. Nitration does involve the nitrogen atom, but it's not the nitrogen atom alone. In nitration, we use nitric acid as a reactant and sulfuric acid as a catalyst in order to attach the NO2 group to the benzene ring. The NO2 group is commonly referred to as the nitro group in organic chemistry. If you've heard the term nitro before, it's probably in a setting where it's meant to imply that a lot of energy is released or that something's explosive. And in fact, many explosives that we use, whether in mining, in industry, or in the military, use nitration in order to get their explosive power. One of the most classic examples is trinitrotoluene, better known to the public as TNT. Trinitrotoluene is a toluene molecule, benzene with a methyl group, and 3 nitro groups that have been attached to it. It's essentially a tetrasubstituted benzene. Other explosives that use nitration are things like nitroglycerin and dynamite. There's also RDX explosives, including C4 and others. So nitration is a reaction that nitrates the benzene ring. It adds an NO2 group to the benzene ring, and that usually creates a fairly explosive molecule. The last reaction we're going to look at is another simple one that involves adding to the benzene ring. It's called sulfonation, and like with nitration, it involves adding both sulfur and oxygen to the benzene ring. To do a sulfonation reaction, the reactant in question is sulfur trioxide, SO3, with a catalyst of H2SO4. This one's a little tricky because the end result is a benzene ring that contains what's called the sulfonic acid group. The sulfonic acid group is really just SO3H, but it's used in a lot of settings, and one of the most famous is in sulfa drugs. You may have taken a sulfa drug if you've ever been on fairly strong antibiotics. And in fact, one of the things we notice about sulfa drugs is that when you open a container of them, sometimes you get the not so pleasant smell of sulfur. That comes from the sulfonated aromatic compounds, which occasionally have sulfur either as a byproduct or they release sulfur as they start to age. That brings us to the end of our aromatic compounds lecture. Be sure to ask me if you have any questions.